Catalysts are commonly used in the chemical and petroleum industries to increase reaction rates, sometimes making certain previously unachievable products possible. Acids, through donated protons, H+, are common reaction catalysts, especially in organic chemistry. Catalysts take part in the reaction, but are not consumed. Many metals like platinum, iron, or nickel also have catalytic activity. Methyl catalysts are used in automobile catalytic converters to reform carbon monoxide, CO, and nitric oxide pollutants, for example. Great Point Energy devised a catalytic gasification system called Blue Gas technology, which evolved from development efforts by Exxon and the U.S. Department of Energy, DOE, in the 1970s and 80s. Catalysts in gasification. Catalysts can be used to enhance the reactions involved in gasification. Many gasifiers must operate at high temperatures so that the gasification reactions will proceed at reasonable rates. Unfortunately, high temperatures can sometimes necessitate special gasifier materials. See discussion on refractory research and development, extra energy input, and cause efficiency losses if heat cannot be reclaimed. One particular problem area is the temperature gap between gasifier and syngas cleanup, which can be several hundred degrees Celsius. Having to drop the syngas temperature so drastically introduces efficiency losses. Approaches to combat this include research into warm gas cleanup and the use of catalysts to lower gasifier operating temperatures. Alkali metal salts of weak acids like potassium carbonate, K2CO3, sodium carbonate, Na2CO3, potassium sulfide, K2S, and sodium sulfide, Na2S, can catalyze steam gasification of coal. In the early 1970s, research confirmed that 10 to 20% by weight K2CO3 could lower acceptable bituminous coal gasifier temperatures from 925 degrees Celsius to 700 degrees Celsius, and that the catalyst could be introduced to the gasifier impregnated on coal or char. The field of catalysis, study of catalysts and their use, is large, and this is just one example. Catalysts that have been used for years in petroleum refining have found use in gasification as well, again to lower operating temperatures. Catalysts can also be used to favor or suppress the formation of certain components in the syngas product. The primary constituents of syngas are hydrogen, H2, and CO, but other products like methane are formed in small amounts. Catalytic gasification can be used to either promote methane formation, a form of which is steam hydrogasification, or suppress it. One recent project, a collaboration between NETL and Research Triangle Institute, RTI, focuses on the catalytic gasification of coal to produce SNG and electricity. The project fact sheet, March 2009, describes the project in more detail. Disadvantages of catalytic gasification include increased materials costs for the catalyst itself, as well as diminishing catalyst performance over time. Catalysts can be recycled, but their performance tends to diminish with age. The relative difficulty in reclaiming and recycling the catalyst can also be a disadvantage. For example, the K2CO3 catalyst described above can be recovered from spent char with a simple water wash, but some catalysts may not be so accommodating. In addition to age, catalysts can also be diminished by poisoning. Many catalysts are sensitive to particular chemical species which bond with the catalyst or alter it in such a way that it no longer functions. Sulfur, for example, can poison several types of catalysts including nickel, iron, palladium, and platinum. Demonstration and early commercialization. Exxon built and operated a process development unit, PDU, to demonstrate the performance of their catalytic coal gasification to synthetic natural gas, SNG, process at Baytown, Texas, in 1979, using bituminous Illinois No. 6 coal. Figure 1 shows a simplified flow diagram of this 1 ton per day, TEPT, PDU plant. The PDU was fully integrated and included facilities for coal preparation, gasification, gas cleanup, methane recovery by cryogenic separation, recycled gas compression/heating, and catalyst recovery. The gasifier was operated at 1,280 degrees Fahrenheit and 500 sig, using 10 to 20% of potassium salts as the catalyst system, at a nominal combined coal/catalyst feed rate of 132 Ulbs/h. High-pressure steam was also fed at a typical steam/coal ratio of 1.9. Demonstrated carbon conversion is at 85 to 90%, with average methane content in the product gas of about 21%. According to the IEA Bioenergy Report published in 2020, there are 686 gasifiers operating in 272 large capacity facilities with a syngas production capacity close to 200 GeV, which equates to approximately 200 mMOL per facility. Production of liquid chemicals and fuels amounts to about 160 GW. Gaseous fuels, predominantly synthetic natural gas, SNG, amounts to just under 30 GW, and power production corresponds to 10 GW. These impressive numbers are the result of a long-term worldwide effort to reach this level of capacity and maturity of syngas production. However, the use of non-fossil feedstocks, such as biomass and wastes, is more limited and generally shipped to units with a smaller capacity. Of the total gasification plants cited above, there are 100 units using biomass and wastes, with a total capacity of few GeV. Considering commercial biomass and waste gasification plants where the maturity level is high, technology readiness level, TRL, from 8 to 9, these numbers are even lower, 88. In recent years, there has been substantial momentum in the commercialization of low-duty projects based on gasification. Some of these processes are at the development stage, some at the pilot scale, and some have been approved for commercial scale-up in several countries. Commercial-scale waste gasification plants in operation worldwide are provided in Table 5. Most of the existing commercial plants for waste gasification are dedicated to the production of power or combined heat and power, CHP, and are in Europe.